Hi and welcome to Podpadstudios. Today we're going to talk about these. These are electronic speed controllers, or ESCs, things that we use in our robots. Now, before we talk about ESCs, I want to talk about the things that we connect to ESCs, which are batteries and motors. Now, batteries are straightforward. They provide the power that powers everything up. You know, I'm not going to go into how batteries work, but they're very, very simple. Motors-wise, come in all shapes and sizes. Little diddy motors, medium-sized motors, bigger motors, and really big motors, but I haven't got any here to show you. These are the motors. These are the sort of 120 watt, 24 volts sort of thing you'd see in an R2-D2 K9, powering that kind of weight of model. Now, motors, we know what they do. These are brushed motors. That means they've got two wires on them. And even though you see a red wire and a black wire, there's no polarity in a motor. What that means is that if you feed power in one direction, it spins in one direction. If you flip it over, it spins in the other direction. That's how motors function. Now, I want to give you a little demo of something else that motors do. And this is actually really, really important, fundamentally important for what I'm about to talk about. Now here you can see I've got two 120 watt motors. The wires are just connected together. So there's no battery in line, there's no speed controllers in line, it's just two motors connected together. Now what I want you to do is I want you to watch the spindle on this motor here. And what I'm going to do, there we go, watch the spindle on this motor here as I do this. You can see as I turn the spindle on this motor, that motor turns. And I'll spin it in the opposite direction. Spins in the opposite direction. Motors, as well as driving things when they're fed with current, when they're fed with power, also act as generators. Now, what that means is this. When a motor is driven, when power is going into it, it might be turning a tooth belt or a gear, which is driving our robots. But when that power stops being fed to the motor and the motor continues to turn, like on the overrun, or even sometimes in reverse, that motor is generating electricity. It's changed its role from a motor to a generator, and all motors do this. They all act as generators. Now, this is really, really important when we are designing robots and when we come to choose our speed controllers. Now, let's come on to speed controllers. Let's start off, and this gets... let's go back a few hundred years. Speed controllers used to look like this. They were basically just very, very simple variable resistors, and you connected your servo into here. It moved this little arm backwards and forwards, and that controlled your speed. You had slow, medium and fast, and that was connected to your battery and then connected to a giant ballast load with some form of heat sink over it. And I'll come on to why that's there in a minute. Modern versions of that are these. All come in different guises, different kind of ampage, so you can do different voltages into them, you can put different current into them, but basically they're exactly the same as the other one, except they're electronic versions. There's no little arms or anything. The motor is connected there and the battery is connected there, and this is a brushed speed controller, not brushless. So I'm focusing here on just brushed motors, not brushless. You notice there's an extra wire here, and this extra wire is what goes to your receiver. When the pulses are sent from the receiver into the speed controller, it varies the speed of the motor connected to these wires, and that's it. It's that simple. You'll have probably noticed the heatsink on the top here, this little black thing here, and a lot of people fit fans on top of here as well. And as I said, this one's got one as well. Well, why would they have a heatsink on top of one? Well, they have the heatsink because heat is generated. Why would an electronic circuit generate heat? Well, it generates heat because of the principles that we know that this can act in, which is as a generator. So on the overrun, as I said, this works as a generator. It's connected to this, so it's feeding current back into this, and this is then manifesting that excess current that arrives back here in the form of heat. Heat is dissipated into the atmosphere and it's cooled by the heatsink and any fans connected to it. And if you use these, I suggest you do use fans because they do get nice and toasty, these ones. And really, that is the most basic form of speed control. They're great, they're brilliant. I've used them in loads of things, and they're really functional. They're brilliant. Now, let's come on to the more advanced, I say more advanced, different speed controllers. These two are from a company called Dimension Engineering, and this is part of their Sabertooth range. I think that's I don't know what that is. It's either a 12 or a 25, and that's a 60. But basically, these are different from these in that they're regenerative. Now, what does that mean? Regenerative speed controller as opposed to just a speed controller. Well, what it means is this. The energy, the excess energy that's produced from the motor on the overrun, when it feeds back in, isn't dissipated just in the form of heat. Yes, there is a heat sink. Yes, there is a fan. Yes, a little bit of heat is generated, but this wants to use that excess energy, that energy that comes back from the motor, and it wants to use it by feeding it back in and back out into the battery. Now remember the way this works. The battery is connected to the speed controller is connected to the motor. On the overrun, the motor is spinning. We're not putting current into it, so the battery isn't providing current in that direction. The motor is acting as a generator, so current is coming back into the battery, recharging your battery. Regen. That's in essence what it means. I'm not going to go into how it does it and why it does it and all that. It's just that's what it does. Now, one of the questions we're asked, I guarantee it every time we go out with a robot, is why do you disconnect your motors on your robot when you push it around? People say they see me scrabbling on the floor by the bottom of a Dalek, or you know, opening a back panel on an R2-D2, and there's, what are you doing? Oh, I'm disconnecting the motors. Why are you doing that? So this is the reason that you need to do it. This motor, this speed controller, when we push the robot around, we don't have any energy going in. We don't have any voltage being fed into the speed controller and then into the motor. But if the motor is connected to the wheels, which it is, and we push the robot around, the motor is now being spun. Remember when I turned the motor, the other motor turned, it acted like a generator. That energy then comes back through the motor wires into the speed controller. These aren't too much of a problem. That heat is generated in the form, the energy is generated and sent into the atmosphere in the form of heat. However, these need a path back to the battery. So when this is turning and it's putting energy back in here, there needs to be a connection to the battery because the energy has to go somewhere. Let's say, for example, you disconnected your battery. You had a kill switch in on your robot, on the battery, you disconnected it, but your motors were still connected to your speed controller and you were pushing your robot around a Comic-Con or something like that. You might notice some of the lights might even glow on the speed controller. What you're doing is putting loads of energy into the speed controller, but there's nothing connected to the battery outputs because you've disconnected your battery. It has nowhere to go. Think of it in terms of a river with a dam across it. If you put some holes in the dam or put a little gate that you can open every now and again, you can keep the water level below the height of the top of the dam. But if there's no gate and the river is just dammed, the water gets higher and higher and higher till it overflows and it floods the surrounding area. With regards to a speed controller, that might mean that it suddenly has too much current or it gets too hot. You'll notice maybe the fans will kick in and worst case scenario, it will shut itself down. Now they do have protection circuits in, they do shut down, but that's not an ideal situation to be in, having your speed controller shutting down on you, because you potentially then might damage the electronics on them through excess heat or excess current or all sorts of things like that. So how do we solve this problem? How do we use regen speed control with motors, with batteries, in a robot without breaking anything? Really, really simple. I physically disconnect my motors from my speed controller when I push my robots around. I will have in line, let me just pop that off, I will have in line between the wires that come from the motor and the connection to the speed controller, I will have a break. I will have a large multi-plug, something in there that breaks that circuit. Now, some people use switches. They'll put a switch in line between the motor and the speed controller. Some people use relays, which are just electronic switches. Again, it's just an electronic switch. And they put them in line. They will serve the purpose. When you flick the circuit is open. The electricity can't flow from the motor into the speed controller, so it will protect the speed controller. No problem at all. It will work fine. Or will it? Or will it? And this is where you might run into a few problems. Now, this is where you've got to do your maths. This is a 2 times 60 amp speed controller. That's how it's marketed. But really, I don't really care about that. What I care about is what is the peak ampage on each channel. At what point will this shut down? And that is 120 amps per channel. That's 240 amps. So that means these terminals potentially can draw up to 240 amps from my system before the protection circuit in here will kick in. All right, so that's actually quite important to know. Manufacturers, when they make motors, fit them with the appropriate size wires. It's wired into the motor. You can't really change that. So the wire is rated for the motor for the current that will be flowing through it at any one point in normal use or in stall use or however it is. It's rated. But what you've got to remember is this. Each of these motors is feeding into a dual speed controller. If, for example, and nobody would do this, but this is quite interesting. If you were to use a wire of that gauge, which is, as you can see, it's a tiny, tiny gauge wire, and connect that to your positive and connect that to your battery, you might think, that doesn't quite look right on the circuit, does it? Well, you'd be right, because potentially this is drawing 240 amps from your battery. This is what it can do before it shuts down. So this kind of gauge wire is useless. We need to be looking at much, much heavier gauge, 6 gauge, 8 gauge, 6 gauge, 4 gauge wire before we're even close to, restricting the current. And you can see from the terminal blocks, these terminal blocks are designed for this gauge wire. They're designed for heavy duty use. Now, obviously you will need to fit a battery cutoff switch between your battery and your speed control. You have to for 2 reasons. First of all, because your insurance, if you go, your public liability insurance requires that you have a battery cutoff system fitted. And secondly, you need that battery cutoff system fitted to isolate your battery in an emergency in the case of a fire or anything like that. It'd be ridiculous not to do it. And also you would be running current and voltage to your speed controller all the time, which eventually will flatten your batteries. However, the big battery cutoffs are enormous. They rated at 150, 200, 300 amps. They're not, think back to the river again, they're not a dam. As soon as they're closed, the electrons, the flow of current can go through without any restriction at all to the speed controller. So we need cable of this size because potentially the current flowing from here to here is up to 240 amps. Now you might think, well, I don't use one of them. I use a smaller one. But this still has 100 amp current flow. That 100 amps. It's still the same size. The cables are still the same. They're bigger cables. You need to max the cables out to the connections that you've got on these units. So basically, electricity can flow. But that's not where the problem is. The problem comes in on our motor wires. What we do, we should really connect our motors directly to our speed controller. And that's what I do. But I just have a physical disconnect in line. And that physical disconnect is usually rated ridiculously high. So for example, if I'm using a 100 amp cable, my block connect will be rated at 200 amps. Tiffany, for example, uses 300 amp systems on her. The block cases are rated at 500 amps. That's because she's using 500 watt wheelchair motors. Now, that's a physical disconnect. So when it's reconnected, there's no block in the circuit. The electrons can flow through the circuit, no problem at all. Let's say you used a switch. Remember what I said, when it's disconnected, it serves its purpose, no problem at all. But when it's in the circuit and the electrons are flowing through it, this is now the dam in the river. This switch is slowing down the flow of the energy. And what that means is if you're using bigger motors or motors that are generating a lot of current on the overrun and feeding that current back into the speed controller, you are restricting how that energy can flow back in, which in turn affects how this deals with the regen in the circuit. And relays are exactly the same. They do exactly the same thing. They're just electronic switches. You've blocked the circuit. Get rid of them. Put a physical disconnect between your motors. Don't do it with switches and these. Can if you want. Maybe it'd be fine on smaller projects. I don't know. I don't use them because, you know, it seems problematic. You've gone to all the effort, of course, of spending a lot of money on a regenerative speed controller, which you then put all this rubbish in line, which limits its regen capabilities. Why didn't you just go out and buy a speed control like this, which is a fraction of the cost? I mean, I can't remember off the top of my head. I think something like £20 for one of these compared to something like 200 and something pounds for something like this. Use the right tools for the right job. And the same thing with cabling. When you're wiring this stuff up, don't mess around with silly piddly little bits of wire. Go for heavy duty 6-8 gauge silicon based wire that can deal with current. It can deal with, you know, the flow of the electrons through it. Now, just to finish, I think I've probably made my point there. You know, disconnect your motors when you're pushing your robot around. Don't bother with switches, don't bother with relays. Regen works brilliantly when you design your circuit for it to work. If you don't want regen, don't buy one. Buy a different kind of speed control. Interestingly, I had a few problems with one of my regen speed controllers not long ago, and it really highlighted this whole thing I've been talking about. And I contacted Dimension Engineering about this, who are the guys that make these. We also use the Cytron speed controllers as well, which are fantastic. Do I rate them better than these? I don't know, they're about the same. These have got a slightly higher current rating on them. But anyway, problem I was having is it was on one of my tracked robots. And I contacted Dimension Engineering and I sent them all the details. And I said, look, this is what I'm doing. This is the design of the circuit. And they kind of came back to me and said, well, there's two problems in your design. First of all, tracks. Tracks are terrible. First of all, what they do is, of course, when we turn a tracked vehicle, the motor is screaming to draw current, and it's pulling that current from everything, because effectively the motor is almost turning at stall level while it turns. And the greater the grip of the tracks and the greater the weight of the robot, the more difficult that is. And of course, then you need to use bigger motors, which requires bigger batteries and so on and so forth. And that was my other issue that was raised. I was using heavy gauge cabling, not a problem. You know, I couldn't get any heavier gauge cabling onto my speed controllers than what I was using. Obviously, I'm not messing around with relays and switches and that nonsense in the circuits. But one of the weaknesses in my circuit was, believe it or not, this. Now, obviously on my robots, I'm using robot batteries a little bit bigger than this. Tiffany, for example, uses a 24 volt, 50 amp hour LiPo Li-Fi battery. And given that she weighs 300 kilos and she's running 500 watt motors, that's 1,000 watt motors, it seemed logical that, you know, that sort of speed controller would be suitable for, you know, that application. The motors probably need to be a bit bigger for Tiffany given her weight, but generally she moves around okay in the circumstances that we need her to. What Dimension Engineering highlighted was that the regen with the motors that I've got was significant because they're big motors, and that means on the overrun they're generating a lot of current. My flow of electrons through the circuit was good. So the only thing that could have been causing the shutdown of this, which is what was happening, was the battery was too small. So my 50 amp hour battery is really too small for the circuit. And they recommend that for those kind of motors that I use a minimum of 100 amp hour battery. Now, that then obviously raises questions about physically how do you fit a 100 amp hour battery in a project like that. But it did bring home one thing that, you know, that you need, like I could leave you with, is the right tool for the right job. Now, sometimes I've run, in the past, using these little motors, I've run speed controllers of this size. And really, it's pointless. It really is pointless. This, I think this is a 12 actually, but it's a 12 amp standard, you know, speed controller with something like, I think, a 50 amp peak. Again, it's a dual, which means there's 100 amps it can draw from the battery. Now, in something like K9, for example, he doesn't weigh much. He weighs, what, 20 kilos, 30 kilos? I've got little motors like these. Again, as I said, drawing about 5 amps. A speed controller of that size, 12 amp speed controller, is actually perfect. Because even on full stall torque, which would be 40, 50 amps maybe, that is right at the point of the limit of this speed control, which is kind of perfectly matched. So sometimes it's important to select the right components that go together when you're designing things. It's about circuit design. It's about actually knowing that when you go out and you buy that, or when you go out and you buy that, in essence, they do the same thing, but they're completely different beasts. One is regen, one is not. Your circuit for regen needs to be completely different in terms of its design than it does for a standard speed control. Anyway, I hope that might kind of answer the question, why do I disconnect the motors on the robots? And to highlight the difference between standard speed controllers and regen speed controllers. And, you know, if you want more information, contact Dimension Engineering, contact Cytron. They are brilliant. They are brilliant in terms of helping you design the circuits. And it takes a while to get your head round when somebody says to you, well, you've got to connect a wire into this that is this gauge, and you've got to connect it directly to batteries, and you've not got to use fuses, and you've not got to use relays, and you're thinking everything about you is saying, well, fuses are good, relays are good, they disconnect circuits and they make things safe. But actually sometimes by fitting them, yes, they do make things safe, but you've then completely negated the reason for buying a powerful regenerative speed control. And then when it doesn't work, or it malfunctions, or something goes wrong, it's 99% of the time down to the fact that your circuit isn't designed well enough, or you haven't considered what this actually is. But anyway, there you have it. Electronic speed controls. I hope that helps.